Record.
It's a record button.
All right. Now we're recording. People who are watching the recording, you missed the first two slides, but yeah, okay. So continuing on, what we were talking about is why you should care about ethical ML. And I think once you've been convinced that you should care, and maybe you've thought about your own ethics and about what determines what is good and bad technology, part of actually applying that is understanding the limitations of machine learning. If you don't understand the limitations of the technology that you're using, you're going to end up like those Stanford researchers who made a fool of themselves. First limitation, machine learning is brittle. I think people think that modern deep learning is a powerhouse that can solve any problem, but it's really not. Here's an email that Ali Rahimi, who was a researcher at Google when he got this email, and is now a researcher at Amazon. Here's an email he shared in a conference talk. On Friday, someone on another team changed the default rounding mode of some TensorFlow internals from truncate towards 0 to round to even. Our training broke. Our error rate went from less than 25% to 99.9% error on a standard 0-1 binary loss. Changing just a small detail of their model, not even of their model, but how it's evaluated, completely ruined their training. So machine learning is brittle. Machine learning can't always generalize. Credit to Ben Recht for this image. What they did in this graph here is they took a bunch of models that represented the state-of-the-art in ImageNet classification. If you're unfamiliar with ImageNet, it's essentially you get a bunch of images and you try and classify what the subject of the image is. They took a bunch of models and then they showed it some new images. These images, the new images looked a lot like ImageNet, but they weren't completely like ImageNet. They were a little bit off. And what they saw was a 10 to 15% drop in performance. So models that were 80% good at predicting what's in the image are now, 65% good. That's not very good, nothing to brag about. So machine learning can't always generalize, and in a lot of cases it can't. You actually saw, maybe you heard about like a really famous example. In 2016, a Tesla car crashed on autopilot and killed its driver. And it crashed because it ran into the side of a semi-truck. When they looked at it, they realized that it had thought the semi-truck was a cloud because they actually didn't have any sides of semi-trucks in their data set. So machine learning is brittle, machine learning can't always generalize, and maybe to add on to that, the consequences can literally be deadly. And the last point, and I think this is probably the most important point to take away from me convincing you that you should be ethical in your machine learning, is that machine learning can't learn something from nothing. I think people think they can just throw a deep neural network at a problem and the problem's solved, but it's not. You can't learn if nothing's there. And if you try to, and even if you have good data, machine learning can often be a self-fulfilling prophecy when we attach confidence and decisions to it. Credit to Moritz Hart for the analogy I'm about to give. Machine learning is a Faustian pact. This is like an old tale, and it essentially boils down to a deal with the devil. You tell the devil, I want to predict the future, and the devil says, sure, you can predict the future, but on the condition that the future will look exactly like the past. And that's what machine learning is. Machine learning cannot generalize in the general case, and it can't predict something that you don't tell it how to. And then back to the self-fulfilling prophecy point, consider an example where we are doing college admissions based on machine learning, and we're scanning applications. Let's say a machine learning algorithm that you deploy for that purpose has some discrimination baked in. Maybe it's discriminating against one race. Well, it becomes a self-fulfilling prophecy once you attach confidence and decisions to it, because you start admitting people based on this algorithm. You start admitting people that aren't this race. Those people gain status having gone to college, and then the cycle continues. You are just fulfilling the prophecy that your machine learning predicted. So these are all limitations you need to be careful of. Machine learning is brittle. Machine learning can't generalize, and machine learning can't learn something from nothing and can often become a self-fulfilling prophecy. Okay, so I'm going to pause for any questions. That was essentially the case I had for why machine learning needs to be ethical. Does anyone have any questions so far?
Um, you said that the Stanford researchers said that the self-driving car thought that the semi truck was a cloud. Aren't like machine learning models usually a black box? Like, how do they know that the it thought that it was a cloud?
I think in that particular case, it was the radar thinking it was a highway billboard sign. So it like just filtered out the results as you would want to filter it out.
I'm thinking of a particular case. Yeah, I'm thinking of one that was machine learning in particular with like the deep net on uh, camera images. My understanding is, and this is once again credit to Ben Recht for this example. Um, essentially what he said is they did a lot of like analysis because obviously people were pretty upset. And what they did was they looked at like they have a lot of data on, and maybe DV can tell you more if you're interested, but they have a lot of data on what goes on in the car and how the predictions are formed. Um, I'm not sure if they have access to the raw images, but they were essentially able to tell what it was classified as. Uh,
Hmm.
and, you know, uh, like they saw the image of the crash and they saw that it classified it as a cloud. If that's your question,
Yeah,
as to how they knew it was classified as a cloud.
cool. That makes sense. All right, thank you.
Yeah. Any other questions?
I just wanted to make a comment that regarding like ethics, there was this interesting proposition that's on the ballot in California for ending cash bail. There's like this law they passed, and it's like whether it should be upheld. And that's like another case where when they use algorithms to determine who gets bail or not, there's a lot of issues where like because of a history of discrimination in like sentencing and like policing, that can propagate down to the algorithm, right? Because that's the data it's using to make predictions for bail.
Yeah, definitely. There's a data set from the Stanford Open Policing Project. And if you train models on it, turns out they end up usually being discriminatory against African American people in particular. Um, I think we did that in 189 when I took it. Um, but yeah, cool call out, Praveen. That's good to know. Any other questions or comments before we move on? All right. So the next topic on the agenda is how do we evaluate models? And in parentheses, I have fairly, because you can have a model that is highly accurate but discriminatory. So we want to talk about some criterion that we might make to make our models more fair. So how can we evaluate our models? What do you guys think? Maybe I could get someone to answer this question. What's an idea of how you evaluate a model? Maybe you learned it in another workshop, or maybe you already knew it. It can be anyone, not just a new member.
Loss functions.
Yeah, loss functions is a good one. In particular, accuracy might be tempting. So let's go with that. Is accuracy enough? Any thoughts?
Depends on the situation, and also it like doesn't take into account that some errors are worse than others, right?
Yeah, definitely. Not always. Good job, Praveen. Accurate models aren't always good models, right? Praveen's hinting at something there. I'm going to hint at something maybe a little bit different. A model that predicts a patient doesn't have cancer, and that's its only function, is it says you don't have cancer. That'll probably be pretty accurate. It might be 99% accurate because a positive case is rare. That's not really a good way to evaluate this model, right? You don't really evaluate whether you can detect cancer based on if you can tell 100 people you don't have cancer and only miss one. Accurate models aren't always fair, right? See the Amazon example from before where they had discriminatory hiring practices. I guarantee you they trained that model so that it was accurate. Surely they wouldn't have released it if it wasn't, but it wasn't fair. What's probably more informative, and we can probably think about this intuitively that this makes sense, is that what you really want is some mix of true positive and false positive rate. And what Praveen's talking about is really important here, right? You can somehow control those, you get a really good idea of like, I can control which errors I want to make more often. And right here, I have an example, a few pie charts. On the far right is one with high class imbalance. So fraud detection is the example here. And what you see is like 97.5% of the time, there's no fraud. So if I just told you, you don't have fraud on your credit card, I would be accurate 97.5% of the time, but that's not really that useful. So let's talk about like maybe some other ways we can evaluate models that might work better. In particular, we care about the second point. How do we make models that are fair? And I want to give a setup for this problem. So for this problem, let's consider we're only working with classification, maybe binary classification. I'll use the example of hiring throughout because there's some gender discrimination issues that could come up. And when I say sensitive characteristic, I'm talking about something that you really don't want to discriminate on. So race, gender, age, sexuality, something like that would be a sensitive characteristic. So my question to you guys is, say we're predicting whether someone should be hired or not. One of the features we have access to is gender. Should we get rid of this feature? Like, should we just toss it out of our data set and call it a day? Model's fair, everyone go home. Any thoughts? Okay, I'll just give you the answer. No, the answer is probably no. And that might be unintuitive to you. Let me explain why. Features in a high dimensional space are largely redundant. They often express significant mutual information, which is kind of like correlation, but think about it more generally, like they affect each other. And they can act as proxies for other features. For example, search history turns out to be very predictive of gender. Let me give you an example. So if I'm classifying whether you should be hired or not, and let's say for some reason, I have access to your search history and I have access to your gender. If I just threw out gender and I throw a powerful enough neural network at it, it might learn to find your gender because neural networks can do a lot of things. They can probably proxy your gender. For example, Pinterest actually, it turns out, has like 51% female users. So if I see that Pinterest is in your search history, I'm 51% confident that you're a female. And that's not very confident, but you can imagine if there's a bunch of little things, I could probably end up proxying gender out of that. So you can't just throw out the sensitive characteristics. Oh, I see that someone put stuff in the chat. Okay, sorry, I haven't been looking at the chat, but I have it open now and you guys can type in there. So throwing away a feature won't do the trick, right? We can learn a proxy. Instead, what we're going to do in the next few slides is try to find ways to mitigate the effects of these characteristics on our predictions. Partly by keeping them in the data set, but by more importantly, enforcing criterion on them that allow us to say we've been fair. First thing I'd like to talk about, this isn't a criterion for fairness, but I think it is important to know, and it comes up when talking about criterions for fairness. Something called the receiver operating characteristic, not all that often covered in CS 189, so or not frequent or not reliably. So maybe you'll learn something if you've already taken it. So suppose we have a classifier. This classifier is classifying between two classes, so maybe it's cats and dogs, and for each input, it outputs a score between 0 and 1. We can choose any point between 0 and 1 to threshold our classifier's score. And we say that any value above this threshold is a positive, maybe a dog, and any value below our threshold is a cat. Maybe we could make that threshold 0.6 and every value above 0.6 is a dog, below is a cat. The receiver operating characteristic, ROC, or ROC, I think sometimes people say, plots the true and false positive rates for different choices of threshold. So on the right here, I have a graph of two rocks in the red and the blue. What these are showing is each value on there, or each point, is the true and false positive rate plotted for a different threshold. So maybe I pick my threshold to be 0, and then obviously I say there are no positives. So I have 0 true positive rate and 0 false positive rate. because I've said there are no positives. I can keep moving up and you see it goes all the way up and to the right. The black line here is a random classifier for like comparison. When you're plotting these, you typically put the random classifier's operating characteristic on here as well for like a baseline. When I say random classifier, I'm saying it sees an image, it doesn't care what it looks like, it just says like cat or dog based on a coin flip. Okay, so this is the receiver operating characteristic. This is pretty crucial to understand. So I'm gonna pause and see if anyone has any questions. Okay, so let's move on to like the actual fairness criteria now. So we've discussed a bit of the background, a bit of what's going on. So I want to talk about like, how do we actually ensure that models are fair by some sense of the word? At a high level, how we do that is by first kind of coming to an understanding of what it means to be fair. And I'm going to discuss 3 different ways of interpreting fairness that are all mathematical in nature and all something that you can enforce in your models. The first one, if you've taken CS70, you already know this, is independence. So a nice starting point is at independence. Formally, and don't worry if you don't understand this, like if you haven't taken CS70 or probability before, but 2 variables are independent if the distribution of one conditioned on the other is the same as if it wasn't conditioned on that at all. So it's unconditional distribution. More intuitively, 2 variables are independent if knowing one doesn't tell us anything about the other. So let me give you an example. The fact that I ate cereal this morning is independent from whether it'll rain tomorrow. You knowing that I ate cereal this morning does not tell you anything about the weather forecast. So those are 2 independent variables. How do we turn this into fairness? Maybe we try to make our classifier's score independent from the sensitive characteristic, like gender. So we can say like, if we're outputting a score between 0 and 1, we want that score to be independent of gender, right? And that kind of makes sense. Like intuitively, that's how a lot of humans would define fairness, is that it just doesn't even matter. It's you know, in some sense, like equal. Independence is kind of like equality at a philosophical level, I guess. So for the hiring example, we want to choose a classifier based on our receiver operating characteristic such that the candidate's gender is independent from their hiring score. So women get scores of like 0.7 just as often as men, right? That kind of makes sense. But we have some issues with independence. This is a pretty good one, actually, I will say. Like if you're gonna start off, independence might be a great place to start. And you can see if that just ends up working. But it has really subtle issues when it comes to small data situations or highly imbalanced data. So suppose historically a college only admitted members of group X and have little admissions data on group Y. If they train a classifier with independence enforced, the classifier is going to admit as many members of group Y as of group X. But this has the problem that the lacking data of group Y, because historically they've only admitted group X, will make the classifier not too great for members of group Y. This can lead to people in group Y getting a bad reputation as being falsely admitted. And I mean, we see this in all the political charge behind affirmative action. Imagine if you, instead of putting a human behind that decision, put a machine learning algorithm behind that decision. You can imagine it'd probably be, you know, people would be even more up in arms about it. So independence is good, but it does have issues. And the other 2 criterion that we're going to talk about kind of try to solve this problem in a little bit different of a way. Does anyone have any questions about independence though, before I move on? Joey Haynes says it's also independent of me eating soup. Yeah, I like soup.
Oh, okay, I have a question.
Yeah.
How do you make your sensitive feature independent from your score?
Yeah. Great question. I actually have a slide where I kind of talk about that, but there's essentially 3 things you can do. And it all has to do with when you decide to intervene with your model. First thing you can do is before you train anything, you can just do some feature engineering. Try to make your features orthogonal and independent and whatnot. There's a lot of math behind that, but at a high level, you can make your features independent. This has the drawback that your features may not be as expressive, and it may be hard to learn off of that. Second thing you can do, second point of intervention, is during training, you can fold this independence criterion into your optimization problem and have the machine learning algorithm optimize around that. That has the issue that like you're constraining what your model can be. You're constraining your space of possible models to be not just all models, but all models that satisfy this criterion. So you may not get a super expressive model. Third thing you can do is look at your receiver operating characteristic. So this is third point of intervention after it's been trained. The thing about this is it works for like a black box classifier where like you have no idea how it works or how it was trained, but it outputs a score. You can find a score on there that's independent. And let me go back to that slide. You can actually also look at scores under your curve as well. Anything on or under your curve is a characteristic that you are able to implement with this model. It's just that if it's not on the curve, you actually have to be random a little bit in your decisions. So if you want to do it like that, you might have to introduce some randomness, which could be pretty like morally bad, right? Because you don't want to be like randomly admitting certain candidates. That's pretty shady. But yeah, so to answer your question, those are the 3 points at which you can intervene with the model to enforce independence. And that's true of the other 2 characteristics that I'll talk about. Does that answer what you're asking?
Yeah, it does. It does. Thank you.
Cool. Any other questions? Cool. Next thing is separation. Oh, okay. My Google Slides transition skills are not that great, so you can see some math already on there, but ignore it for the moment. Separation is kind of this idea that like, okay, independence is fine, but like maybe there's actually something there. Maybe we do want this sensitive characteristic to be allowed to correlate with and depend upon our score. For example, insurance companies would argue that knowing someone's age is really crucial to them making an accurate estimate of like how much they should charge this person. And that makes sense, right? Like elderly people get sick more often. So there's a totally reasonable, fair reason to need to do something like separation. So formally, separation is, and now you can stop ignoring the math on the screen, it's that the score is independent from our sensitive feature given the true label. Let's break that down. So it's essentially saying that like, given that we know the label, whether or not they should have been admitted or not, our score should be independent from the sensitive feature. It can still correlate with the sensitive feature, like gender can correlate with their hiring score, but only if that correlation is completely explained by the label, whether or not they should have actually been admitted or the true label. Essentially what this ensures, probably more easy to understand, is that different groups have the same false negative and false positive rates. So they are rejected and accepted falsely the same, regardless of group. And that's where the fairness kind of comes in, right? Like you can imagine, okay, I want the classifier to be just as bad for me. Sorry, my headphones just died. Give me 1 sec.
Can you guys hear me? Okay.
We hear you.
Yep.
All right. Yeah, sorry, my headphones died. Anyways, this is like, that's where the fairness comes in. Like you can kind of imagine like, I want the classifier to be as bad for me as for any other sensitive group that we might be talking about. And so this is really like, whether our model is right or wrong shouldn't depend on the characteristic like gender. Yeah, and here's an example of Devang, to answer your question, how you actually enforce these things. Separation is a really good example of something you can do after the fact by looking at your a receiver operating characteristic. So if you see here, I have plotted 2 receiver operating characteristics for 2 different groups. These could be 2 different races, genders, whatever you want. It turns out their intersection will satisfy separation. And you could probably think about it long enough and convince yourself. Not only that, but anything under both of the curves, this red region will also satisfy separation. So if you pick a classifier anywhere in here, then you're going to end up okay. You'll have separation. It's just that anywhere under the curve, once again, you're going to have to start randomizing your decisions based on this classifier, which once again is morally questionable. So, okay, so that's separation, kind of equalizing false negative and false positive rates across sensitive groups. Any questions there?
I guess that does feel a bit weird, right? Because basically it's like if you have a classifier that's more accurate for one group than another, you can achieve separation by just making it worse. But yet that doesn't feel like you've made it better.
Right. And that's the tricky thing. One thing I don't mention in this presentation is, and here's like the real kicker that makes this like a really tough problem. There's 3 criterion we're going through. Each of them have some trade-off, and you're probably thinking like, oh, wouldn't it be great if we could get the best of both or best of all worlds? Well, bad news is you can't. You actually can provably not enforce any 2 of these at the same time, let alone all 3 at the same time. So yeah, Praveen, it is kind of weird. You see some like serious downside here that could probably be made up for by another one of these criterion, but it can't. Yeah, that's why this is a really hard problem, but really good call out, Praveen. Anyone else?
I'm having trouble like reading this ROC curve. Like I don't understand how 8 corresponds to both of them having the same true and false positive rate if it's there.
How this intersection does?
Yeah, I don't exactly understand how to read the ROC curve at all.
Okay, so in terms of why they have equal true and false positive rates, it's because that's what you're plotting here, true positive rate versus false positive rate. So if they intersect, they have to. As for how to interpret that, I think maybe I should go back to what the ROC curve is. So it's, you choose a threshold between 0 and 1. You measure the false positive and true positive rates given that threshold, and that is 1 point on your curve. Okay, that's kind of the key here to understanding it, is that's 1 point on your curve. To get the whole curve, you have to go through all the possible thresholds, evaluate the true and false positive rates, and then you plot all of those points. So you've essentially tried all the thresholds, seen the false and true positive rates, and then plotted that. This intersection then is a place at which the characteristics for each of the 2 groups intersect. So it's a point at which both the true and false positive rates are equal. Does that answer your question?
Yeah, it does. But I don't understand how the entire region itself is. Yeah, it has the same false and true, false and true positive rates for both groups.
Yeah, the point here is that like, okay, let me explain. So like any point in this 1 by 1 box, the whole thing can count as separation because it has the same true and false positive rates. But what I've highlighted here are the ones we can achieve with our classifier, right? These 2 curves are characteristics of the classifier we've trained. And it has its own limitations in how good it is and the true positive rate it can achieve. So given that, we're essentially using this ROC curve, like we take the classifier as a black box and we're trying to choose a threshold that gets us a desirable property. And everything under the red region is something we can do given this classifier. Does that make sense?
Yeah, that makes a lot more sense. Thank you.
Yeah. Any other questions? Cool. And feel free to stop me at any time if you have questions. Okay, last thing we're going to talk about for fairness is sufficiency. So sufficiency is kind of another criterion we can say, we can try and enforce on our model and then say it's fair. So sufficiency, first we need to start off by defining something called precision, which you may not have seen before. Precision is the probability that a ground truth is positive, given that a classifier predicts so. And I have that written formally here. So it's essentially like, given the classifier gives you a prediction of like, that's a true positive, you're evaluating what's the probability that it was right. Okay, so that's precision. Sufficiency says that, and this is very closely, kind of intuitively at least, tied to separation. Sufficiency says across all groups of a sensitive characteristic, we want the precision and negative precision, which is kind of an overload of the term, but that should be negative predictive value. That's just the probability up here with 1 switched out for 0 in both cases. It wants the precision and negative precision to be the same for all groups. So that is, the model has the same chance of being right across both groups. And that's kind of a loose interpretation, but just stick with it for now. The model is just as likely to be right about hiring a male as a female. That's kind of an interpretation of this. So that's what sufficiency is, and it can be enforced in the ways we talked about before. And I have this graphic over here to illustrate precision and a related topic called recall that we're not actually talking about right now. But as you can see in this graph, precision is just the number that you predicted to be true positives over the number of positives you were right about over the number of positives you predicted. So it's this green half of the circle over the green plus red half. Just for context, because it's like useful to know for machine learning in general, recall is a very similar, or in a similar vein, is the number of true positives you predicted over the total positives. So the number of true positives you got over the positives that you mispredicted. So that's precision and recall, but as for how it relates to fairness, sufficiency just tries to ensure that the precisions are equal across groups. Does that make sense? Does anyone have any questions?
Is there like a good example of where sufficiency would differ from separation?
Yeah. Oh man, it's been a while. It has to do with like calibrated classifiers. I can send you some links about this, but I'm not sure I have one off the top of my head. Sorry about that. Yeah, sufficiency is very tied to a concept called calibration, which is essentially your score can be interpreted as a probability. And in there, you can kind of see more about what this is and how it differs. I think yeah. If I like work through some like extreme cases, like they're like the prediction is going to differ by some amount, right? To get the equal, false, positive, negative. Yeah. You're essentially predicting the other side of this conditional probability with separation, right? Like you're trying to get your y hat given y to be good versus y given y hat. And as you know from Praveen, since you've taken 70, like Bayes' rule ties those together very closely. So there is a lot of overlap here, but I can definitely send you some resources about calibration and sufficiency. Any other questions? Cool. So a summary of fairness before we dive into interpretability, which is our last topic of lecture. Fairness criterion we discussed. Independence, our classifier gives the same score distributions across all groups. Separation, classifier has the same false negative and false positive rates across groups. And sufficiency, our classifier is just as likely to be correct for one group as any other. As Praveen mentioned, the last two are pretty closely tied. How can we enforce these in practice? I talked about this before. Feature engineering, we can force features to be independent of our sensitive characteristic. Training regime, we can fold this into the optimization problem. And there are like some pretty practiced techniques that, you know, you can use to put in like something that may be hard to differentiate like this. I don't really know much about that. I think Joey Haina might be able to have some ideas about that, but yeah, you can definitely do this. Post-processing, once again, analyze your operating characteristic and pick a threshold that satisfies your criterion. And then one thing I didn't mention, because it's not really about fairness, but I think you should read about it, and I've linked it in the slides, is the F1 score. If you're not going for fairness, like if you're okay with like, or maybe your data doesn't depend on a sensitive characteristic, this is still something you should evaluate because it's much more like, it's much better in scenarios where you have like imbalanced data or really any problems with like your data set. F1 score tends to be just better than accuracy in general. I won't go over it now, but I've linked it. Let's see. Yeah, that's the last slide on fairness. Does anyone have any questions before we move into interpretability, which I promise is a short section? I know this has been about 40 minutes so far. Okay, so we'll move into interpretability now, but last point, I hope what I've proved for you so far is that ethical, fair ML is very important, not only for just not getting sued, but like so that you can like build good technology that helps people. Hopefully that's the ultimate goal, but if not, maybe I've started swinging you in that direction. And then the second point is that you can achieve this in ML without too much difficulty. Okay, moving on. So the last main topic is interpretability. There's a lot of work in this field, and I'm not going to lie and tell you that it's something I'm like super well versed in. I know a fair amount about it, but as a result, I've basically highlighted two methods that constitute like a pretty good survey of like how you can do interpretability. That being said, I've linked some survey papers and a blog post that give a lot more detail about interpretability. Okay, so first point, machine learning is alchemy. That's a pretty bold claim, and it's not mine. It's actually Ali Rahimi's, who I talked about earlier. This is in, I think, a conference talk that he said this. There's a self-congratulatory feeling in the air. We say things like machine learning is the new electricity. I'd like to offer an alternative metaphor. Machine learning has become alchemy. It's pretty bold. Okay, but maybe something that I like a little bit better is from Ben Rex. When I was taking CS 189, he said the following: machine learning is alchemy before alchemy became chemistry. Right, and that kind of makes sense. Alchemy before chemistry was just people doing chemistry without knowing why or how it worked. But machine learning kind of follows a similar pattern right now. We don't know a lot of why the things we do work, and we don't know how to improve them optimally as a result. Do we understand machine learning? Any thoughts?
We try to.
We do try to. Does anyone think we do a good job?
I mean, if the model's simple, we can probably understand machine learning. Like if it's like a nice linear model, then yes, we probably understand it, but otherwise it's pretty hard to keep track, especially when we have something that's super deep.
Spot on. Sometimes, as Devang said. Linear regression, pretty interpretable. Decision trees, also pretty interpretable. Sometimes not, right? Batch norm. A lot of you have probably heard of this, or at least know an idea of what batch norm is, but I'll give a quick summary. So batch norm is a technique for training deep neural networks that improves training by like speeding it up. It gets gradients through faster. And the original paper that introduced it claimed that it reduced something called internal covariate shift in between layers. You don't really have to like know what that is to get the point I'm about to make. But future work found that that's not true. Not only does it not do that, it increases internal covariate shift in some cases, and its benefits weren't even remotely like that. It turns out that batch norm just smooths the optimization space and makes it easier for the optimizer to navigate it. But, you know, uninterpretable machine learning leads to uninterpretable theories. Here's a classic example. Like you'll see this in any deep learning class you take. Maybe you've heard of adversarial examples before, but this is a big reason, or this is a big example of why machine learning is uninterpretable. On the left, we have a picture of a panda, pretty obviously a panda, and our model is 57% confident it's a panda. And that's over a lot of classes, so that might be a pretty good confidence. We add a little bit of noise, and we get our model to think it's 99% confident that that's a gibbon. And to us, right, that looks like the same image pretty much. Maybe you could zoom in and spot some of the noise, but essentially what you see here is like, to us perceptually, that's still a panda, but to the model, it's not. And we don't really know why. And this is a huge problem. That's why we need to understand machine learning. So the first thing I'm going to talk about, the first method is kind of simple. And this is what we're going to do in the notebook. It's called saliency maps, and it gets you what you call local interpretability. So that is, it'll get you interpretability for a specific example. It doesn't tell you, you know, this data set looks like this to our model. It tells you this example, the model may be focusing on this aspect of the image or of the sentence or whatever. So the idea is a lot like what Devang said earlier. Interpretability can be gained by knowing how much each pixel contributes to the output of the model. And in a linear model, we have the following form. W transpose X plus B is our prediction. Has everyone here seen linear models or linear regression? I think that was a workshop.
They very much should have.
Oh, did you teach that, Joey?
Yeah.
Okay, then you guys must know it super well. So linear regression, you've seen this, you know it. In a linear model, like Devang said, interpretability is easy, right? For each of our features, we see how it corresponds to the output directly by the weight it's multiplied by. So perfect, linear models are interpretable. But that's different for a complex neural network. You know, it's pretty hard to tell right off the bat looking at one pixel how it corresponds to your output. What we can do in this case for saliency maps is approximate it. In specific, if you remember from Calc BC in high school or Math 1A or something like that here at Berkeley, somewhere you probably learned about Taylor polynomials. And what saliency maps do is essentially approximate a deep neural network with a Taylor polynomial. In specific, it's a Taylor polynomial, and you end up looking a lot like this linear model. That gives W is the derivative of your model output with respect to its input. That just comes out of the definition of like what a Taylor polynomial is, what its first term is. If you need a refresher, go look up Taylor polynomials, but otherwise you can just trust me on this. So W in this you know, kind of like linearized neural network is just the derivative of the output with respect to the input. And that makes our job really easy, right? Saliency is just gained by taking the derivative of our output with respect to each input pixel. And then it's just like a linear model. We can see exactly how much each pixel contributes to our output because we've made it into a linear model. Does that make sense? Do people have questions? I know this is kind of a backwards way of having it explained, but I think it justifies it. Devang says, yo, this is lit. I agree. Cool. If there are no questions, I'll just move on. But the point you should get from saliency maps is that you're measuring the contribution of each pixel to your output by taking the derivative, back propagating it through your network, just like you're training the neural network, but taking it all the way to the input and measuring, you know, what actually affected what we predicted. So that's cool. And we can visualize these. We can make it into a heat map, and you can see, I think this was probably classified as dog, or, you know, it's probably part of a big data set. So they probably had the specific breed, like it was probably classified as Burmese mountain dog. I think that's actually what this one is. And if you actually take the saliency map, you can see what the neural network is looking at to make that distinction. So all they're doing is what I talked about before. Maybe they're adding back propagation into more layers, but at a high level, it's a lot like what you're going to be doing in the notebook. And what you get is this nice looking thing. You can see the network's output prediction was mostly based on the face of the dog, which makes sense, right? Like you can kind of tell what type of dog a dog is by looking at its face. And I've linked the paper here, so when I send out the slides, you guys can read it if you want. Any questions before I move on? Okay, this is the last thing we're going to cover, and I'm going to cover it at kind of a high level because there's a lot here. I linked the paper once again because, you know, it's not that it's super complicated. There's just a lot of detail in how they actually end up doing what they're doing. So highly suggest reading it if you have the time, but the basic principle is what I really want you guys to get out of it. So the idea is, like Devong said, we have a set of interpretable models at our disposal. We have linear regression, we have decision trees. What if we just try to train one to mimic a network that we're trying to interpret, right? We kind of did that with saliency maps. But formally what we do is we train an interpretable model on interpretable features, and that's really important, to mimic the complex model. An interpretable feature, for example, if we're doing text, is a bag of words. If you're not familiar with bag of words, it's just a count of how many of each word are in a sentence or something like that. So if I said the dog ran, I would have a dictionary with like the equals 1, dog equals 1, ran equals 1. That's bag of words. Obviously, that's a pretty interpretable feature. Superpixels in images, also very simple. You may not have heard of it. I suggest Googling it so you can kind of see, but essentially what they do is they break up an image into kind of sets of contiguous regions of pixels, and they're kind of like patches. So you can like, it's almost as if you shredded up an image and then put it back together. A superpixel would be one of those shredded pieces. Also pretty interpretable because it's just a patch that may hold like a face or a hand or a guitar. So the interesting thing that we do is, let's say we have this interpretable linear model, like linear regression. The only thing we input to it is not the original image. It's a binary vector that tells us whether or not certain interpretable features are present. I know that's pretty confusing and there's a lot to unpack here, but what we might do is, and I'll show you on the next slide, is mask out certain superpixels in an image and then set those entries to 0 in our binary vector that we input. Actually, by the way, binary vector, I know some of you might be freshmen and may not have heard this term, but it's just a vector of 0s and 1s. Yeah, and so we feed that into our interpretable model like linear regression, and we just see what comes out. And hopefully it looks like our, or it's a lot like the complex model that we're trying to mimic. And Lime, once trained, we can use these features and mask them out in specific ways to see how the complex model would have changed its prediction. Some advantages, and maybe this will make more sense in a second when I go to the next slide. It's model agnostic. You see here that I didn't assume anything about the model that we're trying to mimic. So this can be used to mimic any architecture of any neural network or anything else. In the paper, they actually mimic a support vector machine, if you've heard of that. It can work for an entire data set or an individual example. So the saliency maps, right? Those only worked for one example. Lime actually talks about extending this to an entire data set in their paper. Disadvantages: simple models may not have the capacity to mimic complex ones. That kind of makes sense, right? It turns out that Lime, if you read the paper, is only trying to approximate complex models locally, like in small regions of the models, it tries to make it look like a line. But even then, it can be hard to approximate. Another thing, interpretable features, like making these binary vectors out of superpixels and bag of words, they may not be as expressive. They may not be able to represent our true input faithfully. And that can be a problem. But Lime does pretty good. Here's some results. So like I said, you take superpixels, which are just patches. If we mask some of them out, like most of them, and then we unmask them and try and see which ones change the prediction of our mimic model, we can kind of see what our complex model is looking at to make predictions. So in this example, in the original image, the complex model was some neural network from Google. It might have been GoogleNet, not sure. But these were the top 3 classes it classified: electric guitar, acoustic guitar, and Labrador. You can kind of see why, right? But once you actually start masking out pixels, you can see exactly where it looks to get these ideas. So if you mask out everything here, the mimic model will tell you it's an electric guitar. And so you know your complex model is also looking at that. Same thing with acoustic guitar. You mimic enough stuff, you pick the right patches, and then you get acoustic guitar. And you can kind of think about like searching which patches to mask out and which to show to try and like maximize scores on different classes. And then if you maximize the head, it sees a Labrador, and that's what it's focusing on for its results here. So this is one example of one image. Lime also, as I mentioned, tried to evaluate data sets with this. So here's an example of a bunch of, I think, like articles is in this data set, and they're trying to classify the articles as Christian or atheist. Algorithm 1 was their naive algorithm, but algorithm 2 finds that the most important features to predicting atheism are the words posting, host, re, buy, in, and that might be something like a weird token or artifact of the training. But the point was, what they concluded was that this was a bad data set. And they were able to do that interpretably by looking at what was important to the end classification with a very simple interpretable model trained on simple interpretable features. So what they've done here is evaluated a whole data set, not just an image, to be clear. Okay, so that's Lime. That's interpretability. I have one last wrap-up slide, but does anyone have any questions?
Is when we convert things, and this isn't related to Lime, this is related to the one before that, saliency maps. When we convert things into a Taylor polynomial, is that kind of similar to PCA?
Oh, that's an interesting question. I would say PCA differs in that it's trying to kind of convert your features into, like, it's approximating a feature set with principal components, which end up being eigenvectors of a matrix. Here, what we're trying to do is approximate a model via the Taylor polynomial. That's an interesting connection. There is something there, though, in that you're like choosing a representation for something complex to make it more interpretable. That's definitely like a really good way to think about it. Yeah, actually, does anyone have anything else to add on that point? Like any connections they see between this and PCA? Okay, yeah, I'm sure you could think about it long enough and see that there's a lot of similarity between a lot of things you do in ML. So, but that's a good point. Any other questions? Cool. So last slide, and then we'll get to the really short notebook. Interpretability is a trade-off. More complex models tend to perform better, right? Like nowadays, everyone's just training bigger and bigger models. GPT-3, if you've heard of it, is huge. If you haven't heard of it, go look it up. Less complex models tend to be more interpretable though. And that's important for the reasons of fairness and being ethical and understanding why your models go wrong. We can try to mitigate this trade-off by approximating complex models with less complex models. Saliency approximates deep nets with first-order Taylor polynomials. LIME approximates deep nets with sparse linear models or shallow decision trees. Importantly in LIME though, we also approximate the features with interpretable features. And that kind of gives it a little bit of an edge. One thing to note though is approximation always comes at a cost, right? You're never going to be able to interpret a deep model with LIME the way you could if you just interpreted that model, you know, as is. If you found a way to like really understand the connections of the neural network, that will always be better than an approximation. But we currently can't do that, so approximation will suffice. Further reading, like I said, this is not like an area of expertise for me, so I've linked some papers that I found useful in like learning more about this and preparing this. Here's a survey paper on interpretable methods and a guide to interpretable machine learning. That's a blog post. And I'll send out these slides so you guys can like click on these links and whatnot. Yeah, okay, cool. That's all I have for the presentation. Any other questions before we do our workshop? All right, cool. In that case, I will stop sharing my screen. Okay, so Alexi wanted me to put you guys in breakout rooms for this, but it's so short that, yeah, we can do breakout rooms. Would you guys rather do breakout rooms or not? It's like, I think I left 2 lines of code for you guys, and the point is more for you guys to like read through it and see the results. All right, we'll just not do breakout rooms because it's so short. Let me send the zip file to the Slack. This might be buggy because like I said, I wrote this. Well, first of all, I stole most of this notebook from someone else. And second of all, the stuff I did change might be buggy. So be patient. Oh. It's not letting me upload to Slack. Okay. It's, let me see. Give me 1 second. Okay, so I sent a zip file to the Slack. Yeah, just download it, open it up, start the Jupyter Notebook. Most of the code is there, like I said, and I added a couple images, but feel free to try it out with your own images. And you can also try playing around with like which, like I said, we backpropagate all the way to the input for saliency. And that's what this notebook is about, by the way. But you can also try backpropagating to like earlier layers. and see how that changes your results. I would definitely try it with other images though too, because the images I tried are not in the data set that the model was trained on, so they may not be all that salient. Yeah, so I don't know, how has Alexi done this before? Does he just let you guys work and hang out and you guys can ask questions? I see a nod. Okay, that is what I will do then. Go ahead and get started. I'll be here to answer any questions. Honestly, like if you just need the answers, that's cool too, because once again, the point of this notebook is to show you that you can do something. There's not a whole lot of technical rigor to it. Oh yeah, also, I know like typically you guys do it now, but when I was a new member, I definitely got burnt out doing the workshop like thing right after learning. So you guys should feel free to just like log off, do this on your own time. You can always message me if you want the solutions.
All right, bye. Thanks, Joey.
See you, Richard.
Richard.